Good morning, students. Today I'm going to see about the Unit 2 Strength of Material. The Unit 2 comprises of the title will be Shear Force and Bending Moment. So that will be a most prominent and important uh, data which will be utilized for the calculation and visualizing the load and visualizing the bending moment with help of both these data for a civil engineering nature. With help of these two values we will utilize and we will predict where we going to uh, strengthen the member and where the member will be safe and what is the uh, location we want to add additional attention to the point. So with the help of this shear value and the bending moment values, we can easily predict that where the load is going to accumulate and where the location we want to add more stronger one. So these are the important direct topic which helps for the uh, civil engineering board to next level. So this will be an important topic. So next we will go through the prediction of shear force and bending moment for a different members by one. So in this unit we will go through the types of beams and the types of loads and the types of supports. So by after that, by applying the load, different nature of load in a member and what will be the shear force and what will be the bending moment variation by a diagrammatic representation. So the diagrammatic representation will be very useful and will be very helpful for the exactly visualization of where the member will going to accumulate maximum force and where the member will undergone a maximum bending moment. So with help of this data we can able to easily make the structure into a safest structure for the long term utilization. So for that we has been taken the member beam. So beam is a flexural member, that is beam is nothing but it is a member which will be prepared by any composition of material. It may be a homogeneous material or it may be a non-homogeneous material. By the composition it may be differ by steel beam or it may be a concrete beam or it may be a RCC, that is steel and incorporated concrete by an RCC beam, or it may be a timber beam, that is a wooden beam, or it may be by varying the materials we will infer the properties of the beam. Similarly, by the type of support it will be deviated into many forms. So first we will go through that beam which will be which will have a varying length and the load as well as cross section. By applying the load, the deformation, that is deformation will going to accumulate in a beam. So the accumulation of deformation will be studied step by step. So these are the predictable variations in a material to occur the shear force and bending moment. So by applying the load, the member will tendent to transform that load into shear force and tendent to transform the nature of behavior into bending moment. So next will be that we going to see about the types of beam by its support conditions. So with help of support condition, the beam has been getting different nature of names as a cantilever beam which is nothing but one end will be fixed and other end will be free. So with help of that cantilever beam, So cantilever beam is will be a direct relationship that one end will be fixed and other end will be totally free. So that type of beam will be represented as a cantilever beam. Next will be a simply supported beam. So simply supported beam, which is nothing but the beam will be rest at both of its end. The beam will be rest at its both of its end. So the type of representation will be, the type of beam will be represented as a simply supported beam, overhanging beam, which is nothing but it is the beam will be supported at any location and the member tends to overhang at any one direction. It may be right side overhanging, or it may be left side overhanging, or it may be double side overhanging. So the depends upon the support condition and the availability of free end. The member has been represented as a overhanging beam. If it is left side freely opened with the two supports, that will be left side overhanging. If the beam with two supports and the another end you will be opened at a free nature, that will be represented as here right side overhanging. If the member will be supported at the center by two supports at a different distance, that is left side will be open, similarly right side will be open. So that type of free supported will be represented as here double side overhanging. So next will be fixed beam. Fixed beam is, that is, the both the ends of the beam will be supported in the fixed nature. So both the ends of the support will be a fixed nature. So next will be a continuous beam. Continuous beam is nothing but the beam will be a continuous nature. It will be supported by n more than two support will be represented as a continuous beam. Will have minimum three supports, maximum it may be in n number of support, depends upon the span of the beam. So the support will be keep on increasing. So that type of beam will be represented as a continuous beam. So first thing is that based on the support condition, we will segregate the beam into cantilever beam, simply supported beam, overhanging beam, fixed beam, and continuous beam. Cantilever beam is nothing but will be one end will be fixed, other end will be free. Next, simply supported beam, which is that one end, that is both the ends will be supported at the ends. Next will be overhanging beam. Overhanging beam is nothing but the beam will be supported at two ends and another one end will be left open. So it may be a one side overhanging, or it may be double side overhanging. Next will be fixed beam. Fixed beam is nothing but the both of its exterior end has been fixed by the support. Next will be continuous beam. Continuous beam is nothing but more than two supports, that is three or more supports will be in the sequential manner. That type of beam is represented as a continuous beam. So we has been gone through the diagrammatic representation cantilever beam. By the definition, the beam with one end free and other end fixed is called cantilever beam. Next will be simply supported beam. By its definition, the beam is supported or resisting freely on the supports at both of its end. Both the ends will be supported is represented as a simply supported beam. Next will be fixed beam. Fixed beam is nothing but the beam whose both ends are fixed or built into a wall. So the ends has been rigidly fixed type. That type will be represented as a fixed beam. Overhanging beam. The overhanging beam, that is, if the beam one or more end positions extended beyond the support, it may be single side extended or it may be double side extended, will be represented as a overhanging beam. Continuous beam is nothing but the beam which has more than two supports are called continuous beam. The supports will be tendent to extend based on the span of the beam. Next will be types of loading conditions. The types of loading conditions will be, that is, By applying the load, it will be represented in the format of point load, uniformly distributed load, uniformly varying load. So the point load, that is the word indicates that point or concentrated load. So the word will itself indicates that the load which is going to accumulate in a point at a pinpointed end. So we will study that load by applying the exactly on one particular point. So that type of load will be represented as a point load. Next will be, so this will be the point load. So the load is applied at one point, that is a load which is acting at a particular point or any concentrated location. So that will be represented as a point load or concentrated load. Next will be uniformly distributed load. Uniformly distributed load, which is nothing but the load will be distributed for this certain span of length, or it may be for the full span of length. So that type of load will be uniformly distributed load. The magnitude value will not vary for a uniformly distributed load. For example, if the load is 5 kilonewton per meter, means for the acquired distance, for a desired distance, the load will be 5 kilonewton per meter. The load magnitude will not varies for the desired length. It may be for a small fraction of span, or it may be a half of the span, or it may be a quarter of the span, or it may be a full span. So whatever may be the span, but the magnitude will not get vary. So it will be a uniformly distributed load. So self weight will be represented as a uniformly distributed load. Next will be uniformly varying load. So uniformly varying load, which is the another format of load. That load will be varies from one end will have a minimum load and another end will have a maximum load. So the minimum end load will be 0 and maximum end will be, maximum magnitude end will be differ situation to situation. For example, if the value of the UDL is 3 kilonewton per meter, means at initial distance, initially the value will be 0 and it will be uniformly varying to the magnitude of 3 kilonewton. So the variation in the load which directly indicates the uniformly varying load. So next will be that we will go through the type of member along with the different combinations of load and different variation of shape, shear force, as well as bending moment for a member. That will be the variations will be get the diagrammatic representations and variations will get varied depends upon the nature of load what we are applying. For example, if we are applying the point load, we will predict the variation by an horizontal nature. Similarly, if you are in for the shear force diagram, shear force diagram will be short form, it will represent as a SFD. So bending moment diagram will be represented as a BMD. So this will be the short form representation, SFD as well as BMD. SFD indicates shear force diagram, BMD indicates bending moment diagram. So if you are applying the point load, the variation will be a horizontal nature for the desired span of length. In the point load, we will calculate the variation for a bending moment diagram, means the variation will be a linearly inclined variation. So linearly inclined variation will be indicates that the applied load will be a point load. Next, if you are applying the uniformly distributed load UDL, that is W kilonewton per meter. So the variation will be that is shear force variation will be a linear inclined variation. For a bending moment calculation, the variation will be a parabolic variations. So by applying the different nature of load, the Variation will also will get varied, depends upon the situations. For example, if we are applying the load W for a cantilever beam by at the free end, that is the load W will be tendency to downward, and after that there won't be any variation of load, so the load will be horizontally will be same. After that we will have a support at the end, the support end value will be W, will be deflected into a rectangular nature. So next will be by calculating the bending moment values, that is bending moment is nothing but force into distance. Bending moment is nothing but it is obtained by a formula, force into perpendicular distance. So force into distance. So the force will be W and the distance will be L. So that is W into L will be the magnitude of the load of n bending moment diagram. So that value will indicates that the total magnitude of load will be WL from the cantilever with the load at free end. We will conclude that we will have the suggestion is that the bending moment will be 0 at the free end and bending moment will be maximum at the fixed end. So that will be the main theory in order to construct a structure. If you want to construct a structure by a cantilever nature, that which we will directly predict that where we has to strengthen that member and where we has to manageably construct a structure. With help of this data, we can able to construct a cantilever beam. So next, with help of cantilever with the uniformly distributed load, the same logical reasoning has been inferred, that is shear force equal to W into L. Next will be bending moment equal to force into distance, that value will be W L square by 2. So W L square will be 2, that is nothing but force into distance. Force will be W into L will be the load in order to convert UDL into a point load. That next will be length will be L by 2. So you will obtain the magnitude of bending moment will be WL by 2, WL square by 2. And along with the variation of nature as a parabolic variation. So that will be the important variation if you are applying the parabolic variation. If you are applying the load, it will be a parabolic variation. If you are applying the load along the uniformly distributed nature, we will predict the variation in the format of parabolic nature. So next, by an hierarchy of additional variation of load by combination of UDL along with the point load, by a combination of the UDL has been accumulated for the entire length of the member. Along with it, we has been applying the load W at the free end. With help of the relationship, we will predict the maximum shear force will be at the support. That is maximum shear force will be W plus WL by 2. That is cantilever with the point load will be W and cantilever with the UDL for the entire span will be WL. So the both the load has been accumulated in a same member. So that type of load will be W plus L by 2. So next will be the variation. The variation will be W L square by 2. So that will be the linear variation because the load has been applied and the nature of uniformly distributed load UDL. So that will be a parabolic variation. So next will be in all the previous problems, we has been seen that the load will be incorporated for the entire span. On the next sum, we will go through the same logical reasoning for a certain distance of UDL. If the load has been applied for a small fraction of distance A, that is a cantilever carrying a uniformly distributed load for a part of its length from the free end. So from the free end, the load has been applied for a distance of A alone. The total length will be L. So we will calculate the bending moment and shear force variations. So shear force is nothing but that is load into its distance. So W into A. So next will be, we will calculate the bending moment variations. So bending moment variation is nothing but force into distance. So force, that is UDL, will be converted into force by load into distance W into A. Next will be the perpendicular distance will be half of the distance of, so half of the distance will be A by 2. So totally the value will be WA square by 2. So this will be the magnitude of bending moment. On top we will have the UDL load. So on the bottom we will predict the parabolic variation. So this will that we want to apply the variation exactly, very clear according to the nature of load what we has been applied to the member. If you are applying point load, you will be get the variation as a linear variation. If you are applying UDL, you have to be very clear that the bending moment variation will be a parabolic variation. So next will be, so for the easy understanding, we will gone through one numerical variation sum, that is a cantilever beam which comprises of length 5 meter and along with a point load 5 kilonewton. So that is shear force load will be acting on downward. So downward will be 5 kilonewton at the location, that is shear force at location B will be 5 kilonewton. Similarly, shear force at A location will be 5 kilonewton. Next, bending moment at free end. Bending moment at free end is nothing but force into distance. So force will be 5 kilonewton. Distance will be 0. So bending moment at B point equal to 0. So this point, the bending moment will be 0. Similarly, bending moment at A point equal to force into distance. Force will be 5 kilonewton and the distance will be 5 kilonewton. So the total bending moment will be 25 kilonewton meter. So this will be the variation, because in this way, in this question, we has been applied point load. So the variation will be a linear variation. Linearly inclined variation. Linearly inclined variations. So by applying the nature of load, we will exactly convert the load into the converted shape of shear force and bending moment by the logics of transformation of load. So next, we will gone through that another format of load for a different combination of member. We will go through another one sum, that is so far we has been seen that a cantilever with along with a single point load. Now we gone through a sum, that is a cantilever beam will have a 3-point load at a distance of 1.5 meter with 300 Newton from the fixed support and 2.5 kilonewton at a distance of from the fixed support with a magnitude of 400 kilonewton. Next will be 500 Newton at its free end. So this will be the different combination of point load at different locations. So these sort of sums will be asked in the university question paper. So next we will gone through the sum by a step by step. First thing we will predict, we will calculate the shear force at a distance of D. Shear force at a distance of D will be WD, that is load at D point will be 500 kilonewton. So next will be shear force at C point will be previously applied load at WD along with its load at C point. So WD plus WC, that is 500 plus 400 will be 900 Newton. Next will be shear force at B point. Shear force at B point is the accumulation of load along with previously applied load at different points. So that will be WD plus WC plus WB, which is nothing but the load applied at D point, the load applied at plus load applied at C point, and the load applied at B point. So the shear force, which is nothing but algebraic sum of all the forces to this point, that will be represented as a shear force. So the algebraic sum of all the forces is one will be 500 Newton and another will be 400 Newton. Next will be 300 Newton. By making algebraic summation, the value will be 1200 Newton. So we has been calculated the variation of load at different points. We has been calculated the variation of load will be 500 kilonewton at D point. So we are applying the load that will be W 500 kilonewton. After that, in the distance from the C to D, there won't be any load. So if the load is empty, you have to draw a horizontal line. After that, at a C point, we has been calculated the load as a 900 Newton. So draw a linear, that is perpendicular line for a magnitude of 900 Newton. Next at B point will be 1200. So the distance from the B point to C point, there won't be any load. It is a empty member. So if it is a empty load, empty span, we has to apply a horizontal load. After that, at B point, we has been calculated the value as a 1200 Newton. So the draw a perpendicular line for a magnitude of 1200 Newton. After reaching B point, A to B, here the value will be with a non-loaded member for a span of 1.5 meter. So the distance will be represented and connected by a magnitude of horizontal line. With the help of that, we will obtain a shape of the shear force. So next, we will calculate the bending moment. So bending moment at D point equal to force into distance. We has a force of 500 Newton. So 500 into distance 0, we will obtain the value as a 0. So next will be bending moment at C point. Bending moment at C point, that is, it will be, that is, load 500 Newton will be traveled to C point along this direction. So it will be travel a distance of 0.5 meter. So that is 500 into 0.5, you will obtain the value as a 215 Newton meter. The deflection will be on the downward side. So in order to incorporate the downward indication, we will provide a minus sign along with it. Next, we will calculate the bending moment at B point. Bending moment at B point is nothing but that 500 kilonewton will be traveled to B point like this. Similarly, the 400 kilonewton will be traveled to B point like this. So force into distance, the force will be 500 into distance will be 1.5. Similarly, minus 400 into 1, the value will be minus 1150 Newton meter at B point. So next, at A point, that 500 kilonewton will be traveled to this point like this. Similarly, 400 kilonewton will be traveled to this point like this, and along with 300 kilonewton will be traveled like this. So all the three forces will be traveled to a point of A. So with the help of that, force into distance, so the force will be 500 into 3 minus 400 into 2.5. Similarly, minus 300 into 1.5. We will obtain the magnitude at A point will be minus 2950 meter. So we has been calculated the value at each locations. So first location D point, the value will be 0. On second location will be 250 Newton per meter. On the top, we will have the point load. So you have to connect by a linearly inclined variation. Next, By reaching the B point, we has been calculated the value as a 1150 Newton meter. So we are connecting the variation by a linearly inclined variation. Next, by obtaining the A point, we has been calculated the value as a 2950. So the value will be 2950. So by connecting this value here also will be a point load. So the value will be connected as a linearly inclined variation for a magnitude of 2950 Newton meter. So this will be a sum which will help the to study the load for the different combination of point load at a different intersection of points. So we will gone through another problem, another sums with the different combinations of load at upcoming classes. Thank you all.